Okay, so today we're going to be going over a board that had no backlight. I finally found a better place to put the camera than where it was before. It was right next to me, so every time I got up to get apart, I had the good fortune of knocking into the tripod and then cursing. So there's this space where there used to be a window where we knocked the window out to install this Chinese restaurant looking ventilation thingy in here, and that is where the camera is right now, sitting between the two rooms. So yeah, you could see my office is a mess. You can get a full view of it now. So yeah, you may be wondering, like, why do I store the paper towels that we get? Why is there a mop bucket over there? And like, when you see this, why don't I have that in the janitorial closet? Why don't I have that in the storage closet? And again, when you're in New York and like a space that's this big costs about $4,000, I mean, you'll begin to appreciate the decisions that I make in terms of space. So yeah, my office, with the $7,000 rework machine and all this diagnostic setup, it sits next to a mop bucket, some boxes, and a big box full of toilet paper. So today we're going to be doing a board that has no backlight. I actually already did it. I'm not going to have as much time for these videos over the next week and a half, 2 weeks, because my technician is out on surgical leave, so I have to do all of the board repairs and all of the regular repairs for the next 2 weeks. So that's going to be fun. So this is a board that had no backlight. I'm just going to go over a little bit of it with you. Not everything. As you can see, I already have it working. I don't know if you can see that. Let's see. What is it that you see? Come on. There. See? Question mark. So that is working. So I'm going to show you what I did in the microscope camera. My desk is a mess. It's always a mess. My desk is never, ever clean. Alright, so you're going to see here is this. Let's see if you can guess where the blown thing was. So let's make sure the camera's the right way. There we go. So that's the LED driver chip over there. This board hasn't really been cleaned yet, so it still looks like crap. Let's see. So right over here was blown. Yeah, those people are fucking salespeople. You need the ABC fire extinguisher. You need the heavy-duty fire extinguisher for your 200-square-foot fucking office. That has, fuck. Over here, you're going to see where I have a wire. That wire is going underneath the chip, and then it's going all the way in here. So this little via thing in the board, it was kind of messed up. So what I did is I filled it with solder as much as I could. I kind of chipped away at it with this to get the nasty part out, and then I filled it with solder, and then I put a wire over there. It's a battery wire coming from the, there you go, one of these things. So this is a dead battery that we replaced for a customer. I kept the old wiring and all that stuff, and that's that. And as you can see, it has a backlight. So just to give you a little bit of the theory behind it, let me open up a schematic and show you what was blown. Yeah, this was an interesting one because that is not really the one that usually blows. Usually what blows is the feedback via. And I can show you what that is in a second, as soon as the screen captures up. Whoa. Did you just see what that just did? That is pretty sick. Okay, so here is the schematic. So I've gone over the backlight circuit countless times already. So I'll just show you what was not connected. So again, the way a DC to DC boost circuit works is you have your standard voltage going through here. So here, this is the standard 12 volts from PP bus G3 hot. That's what this is over here. If you go to the first page, you'll be able to see what power rails come from what. So you may be wondering, what is PP bus underscore SO underscore LCD backlight? If you have half a brain, you'll see that that's 12.6 volts and guess that it's PP bus G3 hot, since that's the only 12.6 volt rail on the computer. But if you don't have half a brain, that is what the schematic here is for. What the schematic is going to do is, if the page down button on my keyboard ever gets to working, oh, I'm there. I'm out of range. I'm like 2 feet away from the computer instead of 1. So this piece of shit Logitech key, it's a K330. Don't buy this piece of crap keyboard from Logitech. And yes, those are new batteries. People always troll me with the batteries. Like, the computer is here. I'm tapping it. The keyboard is here. Like, it has to be over here or else you don't. It's just, that's for another time. Anyway, let's find where the. Here we go. So we're very close to a list of power rails here. So here we go. Where I see in the upper left corner here. So PP bus G3 hot, and then it tells you all the ones that are a derivative of this, and PP bus underscore SO underscore LCD backlight is there. So back to U9701, so I can show you what I'm talking about here. So this is 12 volts, and the way any DC to DC boost circuit works is you have your voltage, the inductor is over here, right in front of that voltage, and then you have a little switch that's going to switch that to ground. Now what's going to happen is when you switch it to ground, instead of asking the electricity to move through here slowly, you're asking it to move through there very, very quickly, which is going to cause, it's just the basic way to explain it is like stopping short in a car. So when you stop short in a car, you're going 50 or 60 miles an hour and you hit the brakes instantly, you're moving forward really, really fast, and that energy is pretty much that energy is going to be boosted. That energy is what's going to the backlight. So imagine if you take all those, all that stopping short over and over and over again, and and you combine it and you store it, and you don't have 12 volts anymore. You get something like 50. I'm not going to go into how a DC to DC boost circuit works here, nor am I going to go into a long-winded explanation of advanced electronics theory. We're just going to keep it short to what I did to make this work, so I can get my $325. So right over here, this was blown. So this is the part that actually switches. The SW here stands for switch. And the via going from this to this was kind of gone. And one of the ways that you can troubleshoot this, as I've always explained in these circuits, if you want to know what's going on in the output of a circuit, if you want to know what's going on throughout a circuit, what you can do is you can take your multimeter and you put it in diode mode, because it's faster than the resistance mode. There's no way to not be captured on camera with it over there, so you might as well just walk by and give up. One of these days, people are going to see that you work here. I know it's embarrassing. Anyway, back to where I was. So one of the things you can do is use a diode mode measurement to ground on the output of whatever power rail that you're interested in. So right here, let's see, let me just put the multimeter in diode mode. You probably can't see that, so I won't narrate. So when I put that over here, I get 0.524. That is a number that is of interest to me because that is a number that is what it's supposed to be. Now, what you can do is you can simply compare working boards to non-working boards and get an idea of what it's supposed to be. So you have working board you measure, and then you have non-working board you measure. Now, there are many different places in the circuit that a fault can occur, and one of the things this will tell you, when you find out where the fault occurred and then you measure the number, now the next time when you get that number, you'll know exactly what the fault is. So usually if you have a number that's between 0.453 to 0.511, the feedback via, which is the one that most often blows, is blown. So that's after the boost. So after the boost, there is this little feedback via that goes to here. And what that does is it tells the chip what it's actually doing. So if that is not there, it's not going to switch and it's not going to boost. Now here what I was getting was 0.561, which is out of range in a different direction. So I looked a little closer and I saw this. So now I have a number in my head for when that happens. So next time, instead of even having to look at the circuit, instead of even having to take the microscope out, I'm going to know when I have a number that looks like that, the first place to look at is not going to be the feedback via, it's going to be the switch. So this is the importance of diode mode measurements. This is the importance of keeping a database in your head or in Excel or wherever it is you know that it's going to be safe of resistance or diode mode measurements to ground every single spot in a circuit so that you can get an idea of where the flaw is and also maybe what the flaw is based on the number you get, and then you compare that to the first time that you troubleshoot it. So again, you don't have to spend 10 or 20 or 30 minutes troubleshooting the same issue that you troubleshooted before if you have a set of points instead of data that you expect at those points for specific problems. You simply go doot, 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 and then there you go. You have an idea. It's a quick way of measuring the whole circuit. So that is what happened over there, and as you can see, my remedy for this was, I love open broadcast software. Have I said I love open broadcast software? So I'm not going to have to put a transition in there. It's just going to work. Let's see what I get on the microscope here. So yeah, I have this wire that I decided to run underneath the chip to the ball, and that about did it. Yeah, 30x, you're not going to see much. Let's see. Get the light up a little bit. Yeah, pretty cool, huh? So right where, if I move even the slightest bit at 30x, it's going to run away. Let's see if I can point this out. So right where the color is lighter over there, well, yeah, I don't have the hands to be good at narrator at this. Try that again. So right over here where the color is lighter on the lower left, that is one part. See? And on the top, where it's kind of more brownish reddish, that is the other part, and that was blown. So right over here was blown. So that little wire bridges the gap, and then you have a working backlight. Now, a lot of the times you're going to be so unlucky, and that's one of the reasons I'm happy about this repair, because I got lucky, is that the actual thing going through the board is gone, and what you're going to have to do to actually fix this issue is you're going to have to poke a hole through the board, then run the wire through the board, and then solder it to the other end, and that is nightmarish hell, and that's bullshit. So I got pretty lucky here that didn't happen, that it was just split in the middle. Again, that almost never happens. That never happens where it splits on the board side. It always splits when it's going into that hole in the board to go to the other side. Because on the other side of the board is the inductor, also known as the coil. I prefer to call it an inductor. Most of the people who call it an inductor know that it's not what goes bad. Most of the people who use the word coil are usually the idiots on the internet who tell you that you have to replace the coil when you have no backlight. And if you're one of those people, again, just start watching these videos and start learning and stop listening to the bullshit that you read on the internet. But yeah, that's about that. I have a working board. I'm happy. I'm going to put this back together so I can collect some money now. Hopefully you learned something.